Okay, welcome. Today's our day of induction. If you're going on to calculus, it's going to be a very important topic for you, but we are just giving you a little taste of it right now. Okay, and the basic idea behind induction is how do you prove that a statement is always true, or a certain rule is a strategy is always true or will always work? So we have to come up with convincing arguments, and we're going to talk about those today. So let's pretend like it's still winter time, maybe back in February when we had that huge snowstorm, and we want some sunny days. And imagine we're given two options. A, you could run 5 miles in the morning and that will give you a sunny day. Or if it is sunny today, then it will be sunny tomorrow. And so take a moment, just think about which one is better if we want to guarantee the maximum number of sunny days. Which one would you choose? So think about why you would choose the option. Okay, and there could be two different reasons. Option B, because once you have a sunny day, every day after it will be sunny. You get this domino effect. Well, that certainly sounds good, but you're still leaving something to chance. Option A, you would have to run 5 miles every single day. That doesn't sound so good to me. So there's, plus and minuses about both of these options. Okay, so let's take a look now about math with these same sort of ideas. So if we have this sequence, and it's an arithmetic sequence because we're just adding one digit every time, this sequence of positive integers. If we want to write a rule for the nth term, well, the nth term is simply a sub n is n, right? The sixth term is 6, the fifth term is 5, etc. So that's an arithmetic sequence. And if we wanted to write a formula for the sum of my n terms, well, that's going to be 1 plus n, right, multiplied by n. Or we more commonly looked at it like this when we did our sequence. So n times n plus 1 divided by 2. And that's the formula for finding the sum of n terms. And if we wanted to prove to someone that this works, how would we go about doing it? Well, plug some values into it. To test it, we could use some sort of visual to see if this is working. And let's go through how do we prove it now. So let's actually work through proving it. So first thing we want to do is, does our rule work for the sum of one term? So if I have n equal to 1, so the sum of the first terms, wherever there was an n in this formula, I'm putting a 1. 1 times 1 plus 1 divided by 2. Well, 2 divided by 2 is 1. So yes, it works when n is 1. And sometimes it's helpful to do it probably more than one way. So that's what we're going to now do with our induction. And we've done this back in Algebra 2. When we had systems of equations, we would do substitution, we could do elimination, we could do graphing, we could do Gaussian, we could use a matrix, lots of different ways to get to the same answer. And what was the benefit for doing that? So think back to, why would we have you do that? Well, we can verify that our answer is correct. So that's why we want to be able to do this, is to verify. So we're going to try that approach. So the first thing we're going to do is, for the same sequence, what is S of 8? So the sum of the first 8 terms. So if we were in person, we would have some group member do it by hand, so adding the first 8 terms together, and someone else doing it using the formula. And we're going to compare our answers. So if we did it by adding the first 8 terms together, we get 36. If we use our formula, so our formula is n times n plus 1 divided by 2. Well, we put the 8 in, and sure enough, we get 72 divided by 2, which is 36. We get the same thing. So that showed us that both ways work. Okay, so now it says, use the answer from part A to find S of 9, the sum of the first 9 terms. Well, if I'm using this answer, what I'm going to be doing, I'm saying the sum of, oops, you can't see that, sorry. The sum of 9 terms is the sum of the first 8 terms plus the 9th term itself. A sub 9 is the 9th term. So my sum of the first 8 terms is 36. The 9th term is just a 9. So 36 plus 9 is 45. Well, what if I used my sum formula instead? Would that still work? Well, the sum formula says the 9th term is equal to n times n plus 1 divided by 2. Well, sure enough, 10 times 9 is 90, divided by 2 is 45. The answers match, so our formula must be correct. So let's turn this over. Okay, so let's take this to a bigger picture, a higher view of what's going on here. So let's say we want to check that sum formula works for all n's. We've checked it up to 9, but we start checking it when n is 1, 2, 3, etc. And we find the sum and compare it to what we got when we plugged it in, and we find that it's matching. How long is it going to take you to check that the formula works for every single n? Well, hopefully you're all rolling your eyes and saying forever, right? It's not fun. You're not going to do that. So here's, again, just stay with me on this part. Let's say you drifted off to sleep as you were trying to show that it works for every n. And when you wake up, you don't remember where you left off. I do that all the time when I'm reading, when I fall asleep. I can't remember where I left off in my book. But let's say that we've checked the formula works all the way up to when n equals k, some value of k. And that may look a little bit familiar to you when we're doing sums of series. What is the sum of the first k terms? Well, we know that, right? We're putting it in. The sum of the first k terms is k times k plus 1 divided by 2. And don't worry about this. This is a step in our process that we'll come back to. But what we really care about is if the formula works for the next term, s of k plus 1. Why do we care about that? This is because we get this domino effect. If the formula works for the next term, it sets off the domino effect. So if it works for k equals 30, then we know that the rule will also work for, that should be a k here, for k equals 31. And if it works for k equals 31, then it must work for the next one also, which would be 32. All right, so hopefully that makes sense. And if it works for 1, and we know it works for the term after it, then it's going to keep working. So let's try and find the sum of the k plus 1 terms without using our formula. Because remember, we already know what the sum of the first k terms is. We did it right here. So what we're going to be doing is looking for the sum of the k plus 1 terms using the sum of the first k terms and then adding the k plus 1 term to that. So here we go. The sum of the first k terms, we already said, is k times k plus 1 divided by 2 plus the k plus 1 term. And the k plus 1 term is simply k plus 1 for this series. Okay, so we've got that. Now could we try and plug in k plus 1 into my formula that I had been using? So this was, let's take a look here. So my formula is the nth term times n plus 1 divided by 2. In this case, my n value is k plus 1. So k plus 1 times k plus 1 plus 1 divided by 2. If we simplify this, this is simply k plus 1. This is k plus 2. So what we have here is k plus 1 times k plus 2 divided by 2. Are these the same? Right? We need to be able to show or prove that these are the same. So let's take a look at all the algebra. Here's what we got when we added the k plus 1 term to the sum of the k terms. So if I wanted to add these two things together, I need a common denominator. So I'm going to multiply k plus 1 by 2 over 2. That's what I have here. I'm going to distribute the 2 to the k and the 1. And I'm going to distribute the k to the k plus 1. So here's what I got when I distributed. And now because we've got the same denominator, I can put these together. So I've got k squared, and then k plus 2k is 3k, plus 2 all over 2. And we might recognize that we can factor that, and that factors into k plus 1 times k plus 2 over 2, which is what we got when we just plugged k plus 1 into the formula. So this is what we had with the formula. This is what we got when we did it recursively, by adding the k plus 1 term to the sum of the first k terms. And this is what is called the induction step. Okay, so let's summarize what we've done here. Oops, let me cover that up so it doesn't look over. Well, let's put it all here. So here is how we do a proof by induction. And the goal is we need to prove that a rule works for all n. We do our base case. The base case means we're going to show that the rule works for n equals 1, and then find the sum of the first 1 terms. And if you look back over here, that's what we did in part 3, or question 3. So that was my base case. I showed that it worked for n equals 1. Then we do our induction hypothesis. We assume that the rule works up to a certain term number, and that term is going to be k. And then we're going to find the sum of the first k terms. So again, that's my hypothesis. Then we do what we call the induction step. We need to show that the rule works for the next term, the k plus 1. We're going to find the sum of the k plus 1 terms using our formula, and we're going to find the sum of the k plus 1 terms by hand, or the recursive method, showing that the sum of the k plus 1 terms is equal to the sum of the first k terms plus the k plus 1 term. And we, again, did that. Right, here was my induction step. And we showed what we got with the formula, and we showed what we got by plugging in k plus 1. So this was my recursive method. This was using the formula. So we found the sum of k plus 1 with the formula, and we did it recursively. And the recursive simply means that you're looking at the sum of the k plus 1 terms is equal to the sum of the first k terms plus the k plus 1 term. And then we used algebra to show that this and this are the same. And then we have to write a conclusion. The sum of the nth terms equal whatever by induction. I don't think I actually wrote a conclusion on here. So we would say that the sum of n terms is equal to n times n plus 1 divided by 2 by induction. That would be my conclusion. Okay, so those are the 4 steps. We now have 2 problems where you can check to make sure you understand it. So pause this video and give it a shot. Okay, so hopefully you've given it a shot yourself before we start looking at this together. So notice we've got the definition of each term and what the sum should be. So again, step 1 is the base case. So I'm going to let n equal 1 and show that what the sum of the first term is. So if I put a 1 in here, 1 squared is 1, and that is what the first term is. So that's good, that works. The induction hypothesis is we assume up to a certain k that s sub k equals k squared. So I'm assuming that's true. The induction step now is I need to show that the sum of the k plus 1 terms is equal to k plus 1 squared. And so when I do that, so this is just using my formula, k plus 1 squared is k squared plus 2k plus 2. Then I want to do it without the formula. So without the formula means this is recursive. So I'm taking the sum of the first k terms and adding the k plus 1 term. So the sum of the first k terms is k squared. I'm putting a k plus 1 into my formula for each term. So that's going to be 2 times k plus 1 minus 1. Distribute here. distribute the 2, and then add like terms. So 2 minus 1 is 1. And we get k squared plus 2k plus 1. Oops, I had a typo there. It's like that doesn't match. There we go. K plus 1 squared is k squared plus 2k plus 1. Okay, so we have shown that the sum of the nth terms is equal to n squared for this sequence. So that was by induction that we did it. The second one here, again, we're going to do our 4-step proof by induction to show that the sum of this series is found by 3n plus 3n squared divided by 2. I do need to know my formula for the nth term, so this sequence is just 3 multiplied by the n. The sum is given right here. So my base case again, I let n equal 1 and then put it into my formula. So 3 times 1 plus 3 times 1 squared divided by 2. That's 3 plus 3. 6 divided by 2 is 3. That is what the first term is. So that works. The induction hypothesis is that I assume it works up to a certain value k. So the sum of the first k terms is what's given to me. And then the induction step is that I want to show with the formula, so if I put a k plus 1 into here, that it works. And I want to show that the sum of the k plus 1 terms works when I do the recursive method or by hand. So I take the first sum of the first k terms and add the k plus 1 term to that. So here's the sum of the first k terms. This is the k plus 1 term itself. Distribute here. I'm sorry, I wanted to add these together. So I need a common denominator. So I multiplied this by 2 over 2. And then distribute. 2 times 3 is 6. 6 times k and 6 times 1 gives me the 6k plus 6 all over 2. Add like terms and put it in the correct order. So we have 3k squared plus 9k plus 6 over 2. Over here, when I put my k plus 1 into this formula, I'm going to distribute the 3. So I got 3k plus 3. And I've got k plus 1 squared. So that gives me k squared plus 2k plus 1. I got to distribute the 3 now. So I get 3k squared plus 6k plus 3. Add my like terms, and I've got 3k squared plus 9k plus 6, all divided by 2. I have the exact same value here. So this was done recursively. This was done with the formula. And now I can say my conclusion. Thus, the sum of the first of the n terms is given by 3n plus 3n squared divided by 2, and I've done that by induction. Okay, that was your introduction to proofs by induction. I hope it makes sense to you.